Hi friend, this is Professor Prashant. Today we are going to start with the fifth chapter, some important topics, important terms which are important for exam point of view. Now we have already finished this chapter 5, but few students are asking me what are the important points from this chapter. So for that purpose I have started this video. In fifth chapter we will directly start with the types of lens, whether it is convex, concave, defined convex lens, defined concave lens, types of convex lens, that is double convex, plano convex, concavo convex, all that part. Then you have different types of concave lens, that is double concave, biconcave, equiconcave. Second is plano concave and convexo concave. All these are types of convex and concave lens. Now next part will be what you have say technical terms like center of curvature, radius of curvature, first focal point, second focal point of convex, concave lens, all that part that will be there in that part. When you have to consider when we draw this ray diagram for convex or concave lens, the lenses are always thin lenses. They are always thin lenses. They are not thick lenses. Next part will be they can ask you to draw a diagram, just like complete the following diagram where they will give you a convex lens where the object is at focus. So draw the necessary diagram, all that part. That kind of question they can ask. Next part will be is very important when the light is incident obliquely on a concave or convex lens, draw the necessary diagram. So when the light is incident obliquely, so image will be formed at focal plane. It is not at focus, it will be formed in focal plane. Now, what is focal plane? It is a line passing through focus and perpendicular to principal axis. That is called as focal plane, right? Next part will be question they can ask in part A, the factors on which focal length depends, right? The focal length, there is a lens maker's formula. Formula is 1 upon f is equal to, this is mu minus 1 bracket 1 upon r1 minus 1 upon r2. So from this we conclude that the focal length depends on two factors. One is the refractive index and second is the radius of curvature. Focal length is inversely proportional to refractive index and it is directly proportional to radius. Now if the question will be, if what will happen to a focal length if the lens is immersed in water. So when the lens is immersed in water instead of air, its focal length will increase. Now from which point we can see, when we consider the lens in air, the refractive index is a mu g, refractive index of glass with respect to air. When you immerse that lens in water, now the refractive index will be refractive index of glass with respect to water. That value comes out to be 9/8. Now since refractive index decreased, focal length will increase, right? Next part will be what will happen if the part of lens is covered, say half part of lens is covered. Nothing will happen towards focal length, only the intensity of light, right? Intensity of image will decrease because some part of lens is covered. So all the light is not entering that part, due to which intensity of image will decrease. Otherwise, focal length, shape, size, position always remain same. That's it about one more thing, differentiate between convex and concave lens. That's it about part A. In part B, generally you have distinguished between real image and virtual image. I think this you have done in last year also. That is a very basic thing. Then they can ask you to draw a diagram when the ray of light is incident. But here they can ask you to draw with 3 ray diagrams. Minimum 2 rays are required, but they can ask you to draw one more extra ray, that is third ray. That kind of question they can ask. Now here you have different cases, like 6 cases are there, and that 6 cases are very important. Now first case will be what? In case of convex lens, when the object is at infinity. Now there are 2 cases, when the object is at infinity and object is at far distance. When the object is at infinity, image will be formed at focus. The image will be, it is real, inverted and diminished to a point. It is real, inverted and diminished to a point. Now what is the application of that part will be a burning lens. It is a burning glass, right? Next will be when the object is incident. When the object is at far distance, right? When the object is at far distance, the image will be formed, right? Image will be at focal plane, so it is inverted, highly diminished and real, right? Now what is the use of this kind of glass? It is again a burning glass only, or a camera lens. This is called as camera lens or a burning glass. Next, when the object is when the object is beyond 2f1, when the object is beyond 2f1, image will be formed between f2 and 2f2. Image will be formed between f2 and 2f2. The size of image will be a little less, so it is real, inverted and diminished. We can say it is diminished. Now next part, when the object is at f1, 2f1, object is at 2f1. So image is also formed at 2f2, right? So in that case, the object ka size and image size is same. So image is real, inverted and same size as that of object. Now what is the use of that part? It is a terrestrial telescope. It is used as a terrestrial telescope. Now when object is between f1 and 2f1, object is between f1 and 2f1, image will be formed beyond 2f2, right? Your image is real, inverted and magnified. The example for this application of this will be slide projector. It is used as a slide projector. Now next part, when the object is at f1, so when the object is at f1, the image will be formed at infinity. It is real, inverted and magnified, highly magnified, right? So the characteristic use of this will be collimator of spectroscope. Collimator is a collector. Spectroscope is a device used to study spectrum. It is spectrometer is a device used to study spectrum, right? So there you need a parallel beam of light. Next part, when the object is very important, when the object is between f1 and O, that is optical center, then the image will be formed, right? It is magnified, right? Same size as that of object, virtual, erect and magnified, right? So what is the use of it? Application will be magnifying glass. Application will be what? Magnifying glass. Then you have concave lens. Concave lens, first case, when the object is at infinity. So when the rays of light coming parallel to principal axis, they meet at one point, and that is called as appears to meet, and therefore it is diverging lens. So the image form will be virtual, erect and diminished to a point, right? Then what is the use of that part? That is Galilean telescope. Same case 1 ka B part, when the object is at far distance, so image will be formed at focal plane. So all these two cases will give you application as a Galilean telescope. Now next part, when the object is beyond 2f2 or anywhere between the lens and the object is placed anywhere between infinity and lens, right? So in that case, your virtual upright image is formed. It is diminished and use will be a myopic eye. It will be used as a myopic eye. Then you have a distinguish between image formed by a convex lens and image formed by concave lens, right? That kind of question they can ask. Now part C, you have mostly sign convention which are used for numericals. They can ask you 2 mark question, state sign conventions of while using a ray diagram, right? While drawing ray diagram. So what is the sign convention says for object? All the distances are measured along the principal axis. Object is always placed to the left of any lens, whether it is convex or concave, right? Next will be all the distances measured along the principal axis. Distances measured towards left are negative, towards right are positive, up are positive, down will be negative. Now in case of convex lens, object distance is always negative, focal length is always positive. Then image distance, if the image is real image is formed, then the image distance positive, but if the virtual image is formed, image distance will be negative, right? In case of concave, all u, v, f, all 3 are negative, right? And v, u is always greater than v. Object distance is always greater than image distance. After that, you have a formula. Linear magnification is defined as a ratio of linear size of image to the linear size of object, which is equal to image distance upon object distance. Now formula we are going to use is 1 by v minus 1 by u is 1 by f, 1 by v That is called lens formula. It is lens formula. Next we have what is power of a lens. Power of lens is the quantity which decide how much the given lens will converge or diverge the light. So power of lens is the reciprocal of focal length. P is equal to 1 by f. Now for convex lens, focal length is always positive, so power is also positive. In case of concave, focal length is negative, therefore power is also negative. Now power is expressed in diopter when focal length is expressed in meter, right? Or that part. Now you have one more question. If you are considering two lenses, if I join them side by side, say one convex, other convex, if I join them, what is the resultant power? It is equal to P1 plus P2. If I use convex and concave, then also it is P1 plus P2. You have to use the sign, actual sign, and you do the mathematics, right? Normal algebra. Okay. Next will be what is magnifying glass, application of lens. There is a diagram in textbook, page number 128. I am referring Selena 2020, in which there is a page number 128, figure 5.56. This ray diagram, whatever is given, there is a mistake in the diagram. So image obtained is a virtual and magnified. So when we say virtual, the ray should be dotted. When I say virtual image is formed, the image will be virtual, that is dotted. Here we have taken dark line, that is a mistake in the diagram, otherwise everything is fine. Here you have a magnifying power. Magnifying power of lens is given by 1 plus d by f. What is this is for convex lens, so it is 1 plus d by f. D is called least distance of distinct vision, which is 25 centimeter for normal human being, and f is the focal length. You can say you can increase the magnifying power, but up to certain limit. There is a limit up to which you can increase the magnifying power, right? This magnifying lens is also called as burning lens, also called as reading lens, because it is used to study or observe small objects, minute objects on that part. Then you have application of lenses. It is all that part we have studied in the different cases. There you have. There is one topic which is called hypermetropia, and second will be myopia. In hypermetropia, the person suffering for hypermetropia will observe that when the ray of light is incident on it, the image will be formed beyond the retina, right? Beyond the retina. So you have to use a convex lens. You have to use convex lens so that the image is formed on retina. A person suffering for myopia, the image will be formed in front of retina. So if you use concave lens, then that light will diverge and it will form image on retina, right? Then you have other things, whatever we have discussed is given. Then last part of this topic will be differentiate between convex and concave lens. There are two methods, by touching method and without touching method. So if you touch that lens, if it is thick at middle, thin at periphery, it is called as convex, and if it is thin at middle and thick at edges, it is called as concave. If you are going by seeing the image on keeping the lens near the printed page, if the latter appears magnified, it is called convex, and if the latter appears diminished, it is called as concave. On seeing the distant object through the lens, if it is inverted image is seen, it is convex, and it is upright image is formed, it is concave lens, right? Then you have, say, numericals based on this form. So for that numericals, you have to use your sign convention properly. Just go through the videos I already uploaded on only numericals, right? Just go through it. That's it for this video. Thank you, students.